Okay, well, welcome to the second webinar of the afternoon. This is if you were there for the last one, the International Stocktake webinar presentation, this is a follow-on from that, where the concept was to go down and do historic case studies. Originally, we planned to do 2 case studies looking at how respondents use Earth observation for specific greenhouse gas inventory activities, and to go into more detail working with them. Part of the questionnaire was to ask respondents if they were willing to participate in a detailed study, because it did require a certain amount of their time to interact with us to put the studies together. And we had 3 GRA member countries expressed such a willingness. So we wanted to look at having 2 greenhouse gas inventory activities, and the 2 selected were change detection, which was, and for these particular ones, Earth observation was the primary data source for that particular activity, and the other one was grassland area. As you can see, for the change detection, we've actually got 2 case studies, one with Mexico and one with New Zealand, and for the grassland area, it was with Canada. So we expanded to doing 3 case studies because we just thought it would be nicer to have, it would give a little bit more contrast amongst the GRA members, to have 2 different looks at change detection. So moving on, the first case study, this is New Zealand for change detection. And New Zealand is in an interesting position, as you can see from this diagram, that the use of agriculture, forestry, and land use is the predominant greenhouse gas contributor, which is unusual for many countries. It's energy, often electricity generation that's a very dominant factor, but not in the case of New Zealand. Before the use of Earth observation was taken up, information was gathered in a non-spatial way via postal surveys, and specifically the National Exotic Forest Description Survey and the National Annual Agricultural Production Survey. So the investigation of Earth observation was triggered by signing up to UNFCCC and the Kyoto Protocol. And as you can see from the negative bar, dark green one on the left, the potential for greenhouse gas removals from the growth of forest planted after the 1990 baseline is an important driver for New Zealand. It has such a strong effect on their overall budget under the Kyoto Protocol. And so the forest management is a very significant driver in the overall approach to change detection. Earth observation also has attractiveness because of the ruggedness of the New Zealand terrain, because there's a lot of problems with accessibility if you're going to visit places or do field studies. There's also a very large number of forest smallholdings, which are difficult to monitor in a consistent way with consistent methods. The work in New Zealand, the first use of Earth observation data was the generation of the Land Cover Database 1, with the data was acquired from the Spot 3 satellite from 1996. The Spot 3 satellite had 20-meter resolution multispectral data, visible and near infrared data. And the 20 meters was fairly important for New Zealand because of those, particularly the small land holdings. However, moving on to the second land cover database, which was compiled from data taken from 2001, New Zealand chose to switch to Landsat 7 data, which had become available. Because of the high quality of the data was free to access. There were 0 costs for the data to pay. And it also, although it has a lower spatial resolution, it's 30 meters versus the 20 meters that have previously been used from spot 3. The benefit was it has a far wider spectral range, including shortwave infrared and thermal infrared information to help with the classification. So that was then perceived as to balance the slight loss in, or significant loss in spatial resolution. Moving on from that, it was understood that there was a requirement to have baseline. So following Landsat, this is before Landsat 7, but Landsat 4 data was used from the period of 1990 to produce the first land use map for 1990 as a baseline. This was also supplemented by the first of the Spot satellites, Spot 1, which was in many ways very similar to the Spot 3 that they'd also already used for Land Cover Database 1, and that was used to fill in gaps with the Landsat 4 coverage. Going forward, the use of Landsat was dropped because there were some problems that developed in about 2003 with Landsat 7. It started to have problems with the scanning of the image, as you can see this example here, where you're getting sort of stripes occurring in it. So for subsequent land use maps under the Land Use and Carbon Analysis System of New Zealand, LUCAS, the land use maps of 2008 and then 2012 both used data reverting back to Spot, but in this instance they went to the Spot 5 satellite that was now available, where the spatial resolution was higher, 10 meters in the multispectral, and an additional shortwave infrared band to help with classification was also available at 20 meters. In terms of processing, New Zealand started with a strong research community which had experience using Landsat data since the 1970s. They had particular issues developing for their EcoSat software system. They had to develop algorithms that could cope with the very rugged terrain because it was getting very large differences in the viewing angle and the geometry of the sunlight striking the land. The processing was optimized by Landcare Research, and then they also had access to supercomputer facilities to allow the processing to proceed in a timely manner. The issues they particularly have, though, ongoing are accurate classification, especially because they critically need to discriminate between harvested woodlands, and which will then be regrown, and deforestation. As you saw from the history, they've been quite a lot of change between different missions, particularly between Spot and the Landsat series. And this does create artifacts because they're using different parts of the electromagnetic spectrum for different land use maps and land cover databases. And also there are different artifacts due to the use of different spatial resolutions as well. Moving to the high resolution data, which is useful for defining and discriminating and viewing the small holdings, the forest small holdings, does have collateral damage, if you like, in that there's an increased data handling challenge involved in that. And New Zealand, because of its climate, does have strong issues with screening out cloud successfully. Currently, and looking forward, New Zealand is evaluating the use of the new European mission, Sentinel-2, which is was launched last year and is just finishing its commissioning and is rolling out. So the first issue they need to look at is how accessible is the data, and how much is it will it take to store it? Because again, this is 10 to 20 meter resolution data, but in about 13 different wave bands. So significantly more data to handle than with Landsat 7 and Landsat 8, for instance. Then there's the alignment of the data, this whole issue of using data from different sensors. And now we're comparing with the current very successful Landsat 8 mission, and how does that compare with Sentinel-2? And then back to the problem of the cloud masking. The Sentinel-2 production system does include a degree of cloud masking, but the New Zealand authorities need to understand if it's fit for their purposes. And also, being at high latitude, there are issues with seasonal changes in sun angle, particularly in the winter. Will Sentinel-2 have the correct gain settings, the correct sensitivity on the detectors during winter? And it has a wider field of view, 10.5 degrees versus 8 degrees for Landsat. So that increases the issue with what's known as bidirectional reflectance. Sentinel-2 also is being evaluated because it offers the ability to discriminate a different physiological response to increasing amounts of chlorophyll concentration than is normally used, because it has wave bands at about in the 700 to 720 and 30 wavelengths, which here on this graph you can see is critical, that when you get high concentrations of chlorophyll in foliage, it causes the this so-called red edge to shift quite significantly, which means you get good sensitivity and a good response at high vegetation levels, which isn't always true with previous methods of estimating vegetation index. New Zealand has also had experience in 2007 using L-band synthetic aperture radar data from the Japanese PowerFar instrument, and they're looking forward to continuing that work and applying that to look for woody vegetation with the Japanese ALOS-3 mission, should that be successfully deployed and used for global monitoring. Now, image processing is also evolving, using more of an image-to-image and a segmentation-based approach and a multi-date-based approach to find segments of the image, parcels of land, for instance, that have shown change. And this should be less susceptible to the problems they have of changing between different instruments. I'd like to give my thanks to Deborah Burgess of the New Zealand Ministry for the Environment for helping me with the case study of New Zealand. Moving now on to Mexico, and again, this is still change detection. And in the case of Mexico, we can see from this graph here that there's about 15% of greenhouse gas emissions are attributable to agriculture, land use change, and forestry. Prior to the use of Earth observation, Mexico collected data from each region via field technicians. The trigger for or the interest in investigating EO is the ability of Earth observation satellites to provide spatially continuous and statistically continuous input, and the potential then also to reduce the scale of the field observations required to do a full national inventory. A particular focus area of interest is agricultural land that is currently idle but has the potential to come back into agricultural use at a later stage. So Mexico has approached looking at Earth observation usage through a project, Spatial Dynamic of the Agricultural Frontier, looking at data between 2004 up to 2014. The first stage of the project, which is completed, went for a national coverage using the American MODIS instruments, which give medium resolution data of 250 to 500 meters for land cover products. Particularly, their interest is in the 250 meter resolution vegetation index product. The second stage then moves from that to look at, in detail, areas of change using higher resolution spot data. So we're familiar with spot 5 from the New Zealand example, but the spot 6 and 7 satellites, which are visible in near infrared, they can push the multispectral spatial resolution down to 6 meters. So that allows us to focus on areas of change where these are too coarse to have been detected or resolved in detail by the MODIS products which we used in the first stage. Now, the shape of the data processing is the standard MOD 13 product, which is the standard MODIS vegetation product, is then used to compile a time series of land cover classification. So MOD 13 gives, I think, a 16-day repeat. So you can build up a time series, and it's that changing the time series that is used to define land cover, and then they look for changes in that land cover from year to year. That then allows the targeting of the high resolution spot 5, 6, and 7 coverage for the study years. And for this, a different classification approach is used, which is multifaceted and based more on looking at the principal components of the spectral signatures, vegetation index comparable to the MODIS one, NDVI, but derived from the spot image channels, and the use of image segmentation and segmentation textures as well. The issues, the biggest one for Mexico is calibration and validation. The historic data sources that they have for calibration and validation are highly diverse, and they have to go through a fairly complex process of verification of the data sources, so that they're approved, so they can be put into a database, which is unified set of observations to do the calibration and validation of the Earth observation information. Some constraints on Earth observation were found by Mexico in terms of as we mentioned, the lack of comparable historic data. For some areas, this is less important, because for areas which are fast evolving, particularly urban areas, where there's a lot of change going on, then modern data which follows the modern protocols and the high resolution Earth observation data are available for those areas. So it's less of an issue for these faster evolving areas. Mexico is also looking at complementary technologies, for instance, the UAVs, and they've used LiDAR, airborne LiDAR, to look at forest density. In terms of Earth observation, they're looking at using these the high resolution spot 6 and 7 satellites. Using different view angles, they can be used to create digital elevation models. And Mexico is also looking at the use of interferometric SAR. We get interference between different scenes of synthetic aperture radar to look for changes in land surface. Disaster management is also another driver for their work, and the Earth observation data that's acquired for that and the techniques have been found to have been useful for the greenhouse gas inventory activities. And finally, I'd like to thank Carly Armanda Ruz from CIAP, which is the Mexican Agri-Food and Fisheries Information Service, for her support in compiling the use case study for Mexico and change detection. So finally, the final use case study, we're now looking at Canada, and in this case, the activity area is grassland. So here's some background to the overall greenhouse gas inventory situation for Canada, and agriculture does appear to be a fairly significant but a fairly small contributor. But to put that into perspective, the Canadian emissions related to agriculture, land use and forestry are twice those of the emissions which New Zealand has in those same areas. In the past, work was done using the Census of Agriculture, which was a census that was carried out, a postal survey type census that was carried out, and particularly relating natural land for pasture as a proxy for grassland. However, as a proxy, it's not ideal. for instance, not all grassland by any means is used for agriculture. The reporting framework used for the Census for Agriculture is spatially imprecise because the location which is given is the location of the headquarters for the particular land management, i.e. a farmhouse, which won't relate that precisely to the actual fields or plots of land that are being reported on. There are also inconsistencies, partly due to self-reporting. Different land managers might classify similar plots of land differently. And then there are temporal inconsistencies, so when there's a changeover of land management, the same plot of land without a change of usage could be reported as having changed. So these are sort of the problems with the conventional use. So when Canada first looked into this in 2006 to 2008, the first fully comprehensive satellite-based inventory of natural grasslands. This covered data from about the year 2000. For this, Landsat was used. The spatial resolution was adequate for most of the agricultural landscapes in Canada, in contrast to the situation in Mexico, where Mexico found that a lot of their plots of land were just too small really to be resolved well using 30-meter Landsat data, and they benefited from the use of SPOT. The data is freely available and inexpensive. It covers the entire country, and as with New Zealand, staff had considerable experience with working with Landsat imagery. Cloud cover required sometimes not the precise date because it was cloudy, so they had to use circa dates for some bits of imagery, and sometimes they had to resort to lower resolution imagery that was more timely and was required at times when there was less cloud. Canada, of course, also runs the RadarSat series of satellites, and these are synthetic aperture radar satellites, which are not subject to the problems of cloud cover. So that was used to supplement the Landsat for their data. Spot data was considered to be too expensive. The interesting case comparison there is with Mexico, where Mexico did use spot data, but the agency that was using the spot data didn't have to pay for it because Mexico has a pan-government agreement with the commercial company that sells spot data. So although it was commercial data, the data cost wasn't a problem in Mexico for the land inventory activity, but for Canada it was. In terms of the processing, so initially it was enormously, it was quite intensive for Canada. It relied upon a lot of visual interpretation and manual digitization. That has been almost completely eliminated through the use of the C5 data mining and classification tool, which uses a decision tree approach to carry out its classification. Ground truthing is mainly taken from insurance cover, insurance information that is supplied to the inventory researchers, workers. And that covers about 85% of Canadian cropland, but for the rest, there is supplementary work by field observations. The issues for Canada the biggest one is really this issue of distinguishing between the native species of grassland from tame species grassland, from, again, improved pasture and hay. In the past, the natural prairies have become quite fragmented from being cropped, but then allowed to revert back to grassland. And in areas of old improved pastland, even for field workers standing in the field, it can be very difficult to identify and distinguish between improved pastland that's partially reverted and original native grassland. And certainly from an Earth observation point of view, they have very similar in optical reflectance characteristics and properties. In terms of its plans and potential going forward, Canada is in the midst of a 3-year program to enable the handling of data from upcoming mission, the upcoming RadarSat Constellation mission, where they're moving from one radar satellite to a constellation of 3 satellites to give far more systematic access to the synthetic aperture radar data and a higher repeat rate. But then there's also the data from the just launched and the expanding constellations of Sentinel missions, which are being launched by the European Union at the moment. Sentinel-2 for optical data at 10 and 20 meters, and then Sentinel-1, again, it's another synthetic aperture radar mission that would complement the RadarSat constellation. Work has also been carried out on the processing that's carried out by Canada, and they've moved from a decision tree classifier to one that's based upon random forest approach, which was shown to have some degree of increased accuracy, but was also far more efficient in that it could process a lot faster. And with the higher data volumes they're preparing for with these new missions, that's quite a critical factor. I'd like to give my thanks to Ted Huffman of Agriculture and Agri-Food Canada for his support. And then moving on to summary conclusions. As we've seen with these 3 case studies, there are common and divergent themes. Similar technical issues have affected all 3 countries, though there have been distinct national land use, landscape, climatic and financial contexts which are different between the countries. All 3 started with information that had to be repurposed for inventory activities, which wasn't ideal and often lacked the spatial attribution that we're moving towards. The common drivers, the need for the capture of more relevant information and improved consistency with the data used, and spatial coverage as well. The selection of observation data based upon historic data availability, accessibility, existing expertise and experience, cost and the ability to resolve differences, and changes in land cover and land use. So we see these same themes coming out. However, the interplay with the different national characteristics, the farm management, the different biomes, the different terrains have led to divergent solutions and answers between the 3 case study examples we've seen. Some common patterns were there's focus has been on visible near-infrared with some shortwave infrared optical data, with SAR being investigated and used to a lesser or greater degree, though more likely to move into full operational use going forwards for all 3 countries. The degree of the processing and the utilization of high-level products varied, though all 3 countries did have their own processing techniques involved to match their national and specific inventory requirements. So there were significant differences in the national contexts, but in spite of that, there was the sheer range of the classification approaches used suggests that there's quite a lot of scope still for joint working by GRA members to establish and to parameterize best practice classification strategies. This probably applies, as we've seen from the international stocktake presentation, to a lot of different areas, but from this in-depth case studies, this was something that clearly came out, specifically relating to classification strategies. And I'd like to acknowledge the support of the UK Department for Environment, Food and Rural Affairs for funding the work, and the strong support of the Global Research Alliance, and again for the webinar hosting by GRAMP. And